Three atomic models. So Thomson discovers the electron, right? He discovers the electron. His atom has electrons in it, right? These are negatively charged things, right? He knows the atom has to be neutral, so he surrounds it with positively charged material, right? And people derisively refer to this as plum pudding, right? These are the plums are the electrons, right? And then this is positively charged stuff. Positively charged stuff. Presumably enough to make the atom neutrally charged, right? Okay. So Rutherford fires alpha particles at this and is surprised that the alpha particles scatter straight back, right? Okay. He discovers the nucleus, right? So then this is, of course, this is the atom that we draw, because who can draw a picture of the Bohr atom? People try, though, right? Okay. So Rutherford's atom is nucleus here, right? Protons and neutrons, and then there's little orbits here. This is the our picture, right? This is if anybody draws a picture of an atom, there it is, right? So many things wrong about it, right? One is that the electrons are just a point in space orbiting, right? In fact, they're a probability cloud. They exist in many places at once. Okay. The second is that we can draw the size of the atom and the nucleus in the same picture. The nucleus is 100,000 times smaller than the radius of the whole atom as defined by the outer edge of the electron shells, right? But anyway, that's Rutherford. And he discovers that by basically scattering alpha particles off it, right? Alpha particle comes in and comes back out, right? It's like, ooh, there's got to be something massive there, right? Okay. And then there's two problems really with Rutherford's atom. The first is that if these electrons really are orbiting, right? If it's actually K Q1 Q2 over R squared, right? That's the Coulombic force equals the mass of the electron times the velocity of the electron squared. This is centripetal force, right? Okay. This is centripetal acceleration. Okay, if you've got an electron and it's here, and then it's here, and then it's here, and then it's here, right? You've got a changing electric field. The electric field is there, and then it's gone, and then it's there, and then it's gone. And that's exactly how you broadcast radio waves. Well, radio waves have energy, right? So this atom, if the electrons are here, and then here, and then here, and then here, okay, that atom is broadcasting energy. It would be a very, very high frequency emitter of energy. If the electron loses energy, it's going to spiral in, just kind of like the International Space Station, right? Okay, it's going to spiral in, and its orbit will decay, and it'll crash into the nucleus, right? Okay, and we know that atoms don't do that. They existed for tens of years. Okay, a long time, 13.7 billion years or something like that in our universe. Right, so this is the problem, right? Is that orbiting electrons have to radiate energy, and then the other problem is that clearly there needs to be like fixed orbits for these things, because we see these spectral lines, right? These atoms are giving off, when you perturb them, when you provoke them, they give off certain energies and they don't give off other energies. But if it actually was planets orbiting the sun, they could orbit it really anywhere they wanted to, and therefore you'd have any energy you wanted if they're transitioning, right? So the fact that it would have to radiate energy, and the fact that it doesn't account for the spectral lines, this is what Bohr was trying to explain, right? Okay, so what does Bohr discover? Well, he didn't discover, but people discovered spectral lines, right? In fact, they even came up with an equation to describe these spectral lines. They followed a mathematical pattern, right? And so what Bohr did was he actually stated, well, okay, so these electrons are in standing waves. The electrons act like waves, right? Okay. right? So this is the de Broglie wave, right? Where the momentum of it is what is it Planck's constant over the wavelength. I really should know that. I'm pretty sure that's right. Okay. And so what he's saying is that the electrons have a de Broglie wavelength, and it's like it's oscillating around the atom, right? And this is very complicated. We can't really draw pictures of this, but people try to, right? You see these little shaded diagrams showing the probability of these things. And it's more bizarre than you can imagine, right? It's that the electron has a probability of being there. In fact, in the ground state, it actually has a probability, quite a large one, of being inside the nucleus, right? It's just a probability, right? Which it doesn't, electrons don't really interact with the nucleus unless you have a nucleus that has too many protons, right? And then it can get rid of a proton by eating one of those electrons. Anyway, wow, I just went on a rant. Electrons act like waves. Anyway, this is what it is, right? And the Bohr atomic model, I think we've solved it explicitly for hydrogen. You get to helium, right? Now you've got a three-body problem, right? Which, you know, in that kind of physics, it's pretty hard to solve the three-body problem. Four-body problem, right? Well, you know, forget about that. Okay, so there's all kinds of problems with even just helium, right? But we've got the idea, right? Wow. All right. Woohoo!